On the bench today is a new vacuum tube voltmeter that I just acquired this week. This is an EICO model 221 vacuum tube voltmeter. I believe this dates from the 1950s era of electronic equipment. EICO sold both wired and instruments in the form of kits, and I believe that this was a kit that was assembled by someone who purchased this unit. It is in reasonably good shape. There's no scratches evident on the case. There's a bit of a film on the unit, so either it was sat in a garage for many years, or possibly it was in the home of a heavy smoker. The meter itself is a little faded, a little dim, but it's not too bad. And the thing that I noticed when I bought it was, you can see the meter flops up and down. It's not stuck in one position, so it's very likely that the movement on this meter is fine. The case is in reasonably good shape on the side and on the back. It's got some scrapes and dings and parts of paint that have come off, but this is probably going on 70 years old at this point, and I hope I look this good at that age. The cord is reasonably supple, but it's not going to last long in my workshop. It's broken here. There's some cracks that you might be able to see along the side, and it just gives me the willies when you look into it like this, with the open face and the strands of the cord wire all over the place. So this is going to go. It's going to be replaced with a modern polarized cord. So before we open it up, let's look at the schematic of this instrument, which is available freely on the internet. You can see it's a very clean and simple circuit. Uses a vacuum tube rectifier. So you have your power coming in, and again, in the days before we had polarized plugs in the United States, this could be either hot or neutral, and so that makes this capacitor right here very critical to make sure that that is a modern safety capacitor. I'll bet you a Coke that that is an original paper capacitor that is extremely leaky, which would make touching the metal case probably not a wise thing to do. But we'll get in and check out the technological anthropology of this and see what updates, if any, have been made in just a moment. So here's the bridge circuit. Nothing to write home about there. The reason I was interested in this, besides feeding my VTVM addiction, is that internally here we've got 5, 9.5, 10 megohms in the DC input section. But then down here, if you look at the probe construction, there's another 15 megs at the tip of the probe. So this is a 25 megohm input impedance meter, which is uncommon from later vacuum tube voltmeters, and is a curiosity to me. So let's open this up and see what it looks like inside, and get down to getting it back into working order. All right, I've taken the screws off of the panel. There are 6 screws on the front, and there's 1 screw on the back of the panel that comes in just right next to the service entrance. And just kind of looking at this first time, it's very interesting that the battery holder is in the back of the case, which is nice, so that if the battery leaks, it leaks into the case and not down over the electronics like the Heathkit designs. It does make one wonder how the battery was attached, since that's a battery clip. It's not really a battery holder. And in fact, the wires that lead to the battery have just been clipped. So we need to install a battery holder there if we intend to use this to check resistance. So let's kind of look back here, and the first thing that should immediately kind of pop up is that there are a number of modern capacitors in here. These orange to red capacitors are new, but there are some capacitors that are old and quite possibly the original. So that one definitely qualifies as that. And if anyone took my bet, you owe me a Coca-Cola, because right here is the capacitor that goes from one side of the power line to the chassis ground. You can probably see right there. And that is a paper wax capacitor. And that is almost certainly the original. It's interesting that usually these things are very waxy and sticky, but this one actually doesn't seem like that. But anyway, I'll clip it out and test it just to see at what voltage it leaks, and then I'll replace it with a type Y safety capacitor. So some other things to look at here. I mean, this was absolutely a kit. This was assembled by someone who wasn't professional. The soldering jobs are, well, they could be better. And you see that through and through, although the person that came through and updated it with these more modern capacitors probably didn't do the best job either. You see a lot of things that are kind of questionable. Here's two capacitors that are, move this up a little bit. Here's two capacitors right here that have been put into parallel and kind of twisted around and then soldered, and there was a substitution made there at some point. These capacitors, these resistors, this resistor here, those look like they're more recent than these capacitors, which seem to be much older. It's kind of interesting. A lot of these things have paper around them with the value of the resistance stenciled onto it. I've never seen that. The paper is loose, so I don't know if that was original or something that someone did since the kit was built. I'm not really sure. Someone has somewhat helpfully gone through and labeled each of these potentiometers as to what they adjust, which is nice. You should never ever trust such labels. You should always verify them with the schematic. Overall, there's no burn marks. There's nothing that looks like it's been corroded. So worst case scenario, if I have to completely rebuild this, although finding 9.5 ohm resistors is really going to be painful, it can be done. It's point-to-point wiring. There's lots of room to get in here and get to the individual parts. Let's look at the top side. In horrors, someone has dumped some sort of sealant over these potentiometers to helpfully, quote unquote, keep them from coming out of adjustment. Although for something that's sealed into a metallic cabinet, it's hard to imagine just how they could come out of adjustment. So I'm not real happy about that. Luckily, it looks like I can just more or less chip that away and clean it up. In fact, it just kind of shatters like, I don't know, like nail polish or something like that. Okay, so that's that. Here are our 3 tubes, 2 that are RCA branded and 1 that's GE branded. Whether or not those are original, I couldn't say. Probably not. So I'll go through and I'll test these on tube testers. The power transformer looks fine. No burn marks or scorch marks or anything like that. And there we go. So let's get down to changing the capacitors at least, and then we'll apply some power and see how that goes, and see if this is kind of minimally functional. And if it is, then we'll go through and we'll test the individual resistors and see how badly those the carbon resistors have drifted out of specification, and we'll move on. I've replaced the capacitor with a modern Y safety capacitor on the EICO 221. And I said that I would test for leakage this Solar brand wax molded paper capacitor. So this is listed at 0.02 microfarads at 600 volts DC. And when I measured it on a modern LCR meter, it turned out to be about 1800 picofarads, which is 0.0018 microfarads. So it's pretty close in terms of capacity. When I checked this on the Heathkit capacitance bridge for leakage voltage, it did pretty well. It didn't leak up until between 200 and 250 volts. So this is, of course, completely unacceptable for the critical position that it's in the circuit from a safety perspective. But I have seldom seen a wax capacitor of that age hold up that well. What I want to do now, I looked this over pretty carefully inside. I've only replaced the safety capacitor. I haven't looked at any of the other resistors or changed the one old capacitor that is remaining. But I looked it over and made sure that it looked like the wiring was commensurate with what it should be on the schematic, and it looked pretty good. So I'm going to plug this in now and cautiously just see how the meter behaves before proceeding with the rewiring. So I've plugged it in, and I'm going to now turn it on. So drum roll, please. No magic smoke, that's always a good sign. So the meter should sway one way and then relax back up towards the 0. There we go there. And it relaxes. You can see it's a little bit out of adjustment, but not too bad. That's purely accidental. And you can see the 0 adjust. We'll move it back and forth. I don't get anywhere near full-scale deflection when I've got the 0 adjust pot all the way up. Not sure that I need to, but we'll look into that later. But so there it is at about 0. And it stays pretty zeroed, independent of the range. So that's interesting. So that's on DC plus volts. There's DC minus. Again, very little slew there. Ohms, that should... well, that's disappointing. So that should fly up all the way to this end of the meter, and I should be able to adjust it with the ohms adjust pot. But I'm not getting that. And then there's the AC volts. So you see when I go to AC volts, the meter deflects just a little bit relative to the DC volts. And again, that's not unexpected. But look at how much farther over on the AC range that it goes. Is that a warm-up issue? No? I think that's an electrical issue. Okay. So I think the moral of the story here is that I need to go through and check all of the resistors, because I bet some critical ones, or maybe even most of them, have drifted out of spec. just for giggles and grins, let's see. This did not come with probes. It was advertised as having the probes. The person who mailed this, the owner, forgot to include the probes, so those are on the way. I will be very excited to get them. Rarely do you have complete probes, but what I can do is I can kind of fake a probe or simulate a probe. Here is a 15 megohm resistor, and I just so happen to have a 9-volt battery. So let me put this on the 10-volt range, and let's just see how this works out. So I'm going to clip that onto the common and touch this here, and so this is the 10-volt scale down here. All right, there's the 10-volt scale. So this should come up to be between 9 and 10 volts. And in fact, I barely get 1 volt. And if I change it to the 5-volt scale, it should peg it. But it doesn't. It only comes up to about 4 volts. And on the 100-volt scale, I should be getting somewhere up around this range, and I don't. It just barely moves it. Okay, so again, this is not unexpected on a device of this age, and just means that we've got more fun ahead of us. What I will do now is I will go through and I'll test the resistors and check the wiring a bit more closely, and see how that goes. And then we'll be back when we've learned something, so stay tuned. I've gone through the internal wiring of this a bit and checked out the circuitry and how it's wired, and spot checked many of the carbon composition resistors in the circuit. And I found some surprises and some things that probably shouldn't surprise me, this being a kit. So first of all, we'll go back to the schematic here. The resistors here, R13 through 17, and then R18 through 22, and then R23 through 25. These have all drifted, and they've drifted very, very significantly. So, we didn't get good readings when we tested our 9-volt battery, and that's part of the reason, but it turns out it's not the entire reason. So, going back to the circuit, you see that this switch right here, so these are the range switches, so that's this one right here. These switches should have 1, 2, 3, 4, 5 positions. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and so on. But now look at this, and I've got this over on its side because it's outside of the case and it's not stable if I set it up right. In fact, there's a position down here that's not marked. So that's position 1, 2, 3, 4, 5, and 6. So they've used a switch that has 6 positions instead of the 5 that are labeled. And in fact, if you look around the back, I don't want to turn it around right now because it's plugged in, you can see that it's this position that is not wired, but these that are. So that means that essentially this is the 5-volt position, this is the 10-volt position, and this is the 100-volt position, and so on and so forth. So I need to change this chicken beak or chicken head knob so that it's over 1. But if we just do that now for our 9-volt battery, so I'm going to bring the 9-volt battery back, I'm going to hook it up here, and I'm going to put it on the 10-volt scale. Now, let's probe it, and look at that. We get something very close to 9 volts. Now it should be over 9 volts. I think this reads like 9.6 volts if I'm not mistaken on a DMM, and this is 8.2 8.6 or 8.8, 8 point something volts. But that's much more in range with what you would expect. And if we move this up now to the 100 volt scale, you see that it's just short of 10 volts on that scale, right? Like you would expect for a battery that reads over 9 volts. So, that was a very nice thing to discover. So we've got to change the resistors. And these are not standard resistors, or at least common resistors anymore. This is 9.5 ohms, 95 ohms, 9.5K, 95K, and 9.5 megs. So if I can't find those on DigiKey or Mauser or wherever, I will have to synthesize those out of series and parallel combinations of standard resistors. And I think someone has done that with some of the kind of kludgy resistor combinations that are in there that have also faded out of spec. So that's that. There are some other things in this circuit that don't make sense. This was, clearly a kit. For example, this 0.01 microfarad capacitor. Someone has changed that and upgraded it and modernized it. But it's not hooked up like this. It doesn't go from one of these switch positions down to ground. This actually goes somewhere else. So it's amazing that this works as well as it does to begin with. There's a mystery as well. Here, this is marked filter capacitor. It doesn't have a value next to it, and you can see that in fact it is. I mean, this is what smooths out the rectifier. And if you go to the bill of materials list, so that's C2, it lists C2 as a filter condenser. Doesn't put, X number of microfarads in. So that's a bit of a mystery. Now, this also is one of the capacitors that's been updated in this unit. And it was updated to a 4.7 microfarad, 350 volt electrolytic capacitor. And 4.7 microfarad strikes me as pretty small for a filter capacitor. Usually you think in terms of things that are 20 microfarads or higher. So I'll have to investigate that and see if I can figure out the rationale behind 4.7 microfarad or whether or not it needs to be bumped up. All right, I think I'll stop this video here and pick back up when I've gone through and wired correctly the kit and replace the drifted resistors. And that will probably be a couple weeks to get those parts in the mail. I hope you found this useful. If you did, please give it a big thumbs up, and part 2 will be forthcoming. Thanks for watching.